squared plus 2 times the acceleration times the distance. And then we've got the velocity initial plus the acceleration times time. And that we know the velocity is the change in position with respect to the change in time. And we also have a definition that my acceleration is going to be the change in velocity with respect to time. In the problem, we were told that the initial velocity was at rest. So my initial velocity is going to be 0. We were told that the optimum takeoff speed was 150 meters per second. And we were told that the distance that we wanted to take off at was 760 meters. The length of the runway was irrelevant. Runways, the reason we have length of runways isn't necessarily for takeoff. We have length of runways for landings. You want the length of your runway for landing. And your difference between, just so you guys know, some facts of information, what's the difference between a regional airport, a national airport, and an international airport? It's the length of the runway. So the length of the runway has nothing to do with whether or not there's a plane that comes from another country. It's all about the length of the runway. And the longest runways, I think, in the state of Oklahoma are at Tinker and at Lawton. You wouldn't necessarily think Lawton, but Lawton has a very long runway. And then Amarillo, Texas has an international runway. And you can land the largest plane in the world at Borger, Texas, or at Amarillo, Texas. I've seen it. It's that Russian cargo plane. It is one big aircraft. All right, so we know the initial velocity, the final velocity, and the distance. What I don't know is time, so I don't have time at all. So any equation that's got time in it, ixnay, not going to be able to use it. So I can't use this one, and I can't use that one, and I really don't have the information to do the other ones. So I'm going to end up using that equation. So if I write that one out, I got v squared is equal to v initial squared plus 2 times the acceleration times my change in distance. I'm solving for acceleration. My initial velocity was 0. So now I've got v squared is equal to 2 times the acceleration times my distance. I get v squared divided by 2 times the distance is going to give me my acceleration. And in this case, it gives me 150 meters per second squared divided by 2 times 760 meters. I'm going to end up in meters per second squared, which is what I want. Okay, just a second. Meters per second squared. And if I plug that into the calculator, I get my 150 squared divided by 2 times, times 760. I get 14.8. I want a show of hands of everybody who's been on an airplane. Okay? If gravity is 9.8, all right, gravity's 9.8, and we experience that thrust of the airplane, what do we feel? We feel the acceleration. So in this case, I could have probably taken a guess without even looking at doing the calculation that the 14.8 answer was going to be the correct one, because I was going to feel an acceleration greater than that of gravity. Because we've all been on a commercial aircraft and we've felt that acceleration. So if you want to have fun about feeling that acceleration, let's do one. If I'm on an aircraft carrier, a buddy of mine was on the Theodore Roosevelt, and on an aircraft carrier that takes, the catapult distance is about 93 meters. The takeoff speed is roughly about 76 meters per second. We want to calculate the acceleration. I'm going to do the exact same calculation. So we figured out that it's v squared divided by 2 times the distance is going to give me my acceleration. In this case, that jet coming off the aircraft carrier, if it just lets the catapult do the work, it's going to go off at 76 meters per second. But of course, the pilot's also going to gun it. But we're just going to use that 76 meters per second. So we're going to use the 76 meters per second. We're going to square that, divided by our 2 times my 93 meters. If I do that, I get 76 squared divided by 2 times 93. And I get something on the order of 31 meters per second squared. Now, we talk about, in acceleration, we talk about G's. Okay, we talk about G's. And what that is if I take my 31 meters per second squared divided by my 9.8 meters per second squared, that's approximately 3.2 G's without the pilot pushing down the accelerator or giving the engine gas, or the jet engine gas. So those catapults will sling you off the aircraft carrier. Taking off, from what I understand, taking off from an aircraft carrier is not the bad part. It's landing on the aircraft carrier. Even helicopter pilots don't like landing on aircraft carriers. So it's just kind of the pieces of information. Okay, so what we've got out there, just so you guys can keep up on some stuff. We will be doing that here in just a second. I'm going to go back here. Do this. Blackboard. Should just get right in. I know I haven't done anything for Tonkawa, so I haven't switched it over yet. All right. Okay. You've got information in here about the first test. The first test will be Wednesday, September the 19th, and it's going to cover chapters 1 through 3. It will cover through projectile motion. I released it yesterday, so if you have alerts on Blackboard, you will notice that there is a quiz. And I went ahead and put in a second quiz because just so that you guys can get more practice at these problems. Don't make these problems harder than they are. These are problems that you guys do in your head. Okay? You guys do these types of problems every day. When you are driving in a car and you pass another car, you've done this problem. I've got soccer people, right? Where are my soccer people? Do I have soccer people? Oh, okay, I got basketball or baseball or softball. I got softball. Okay, so think about this for a second. Person hits the softball with a bat and you're playing outfield, right? You are seeing the ball come off. You are making a mental estimate right then and there of the velocity of that ball, and you are looking at the trajectory of that ball, correct? You are not only doing that, you are making a judgment about how fast you have to run to go catch that ball. That's exactly the type of problems we're doing. All we're doing is putting the math to it. If you're doing basketball, we're about to do the projectile motions. You're sitting at the free throw line. You're getting ready to put this basket in the ball. You're looking at what angle and how much I have to do it. And you've done it a gazillion times, right? You've done it a gazillion times if you're trying to throw in a free throw. That's all we're doing. We are not doing anything out of the ordinary. You guys do these calculations in your head all the time. My daughter is an equestrian. Not only does she do that calculation for herself to go over the jump, she's doing that calculation for her horse to go over the jump. She does that calculation all the time, and she does it without thinking about it. We do it without thinking about it. If you have a pen roll off the desk and you try to catch it with your hand, it's the same thing. That's all we're doing. We're not doing anything that you guys haven't done a gazillion times. All we've done is put the equation to it. All we've done is this. This is the only difference of what we've been doing. There it goes. All I did is give you an equation to describe that motion. That's all I've done. We've just given you the mathematical symbolism to do that. So it's something that you guys have been doing forever.
I have a question. And maybe you guys have the same question. This is my second time around and it's a little bit more familiar. Those will be the formulas that we will use for the problems that we've seen so far, right? Those are all the given formulas so far?
So far?
Okay. On some of the V to the second, stuff like that, I struggled with knowing what to use and when to use it because it was hard to understand what each one of those meant. And I don't know, Hewitt-Druitt, you gave that as a suggestion last semester. That was a huge help. It really did help make this make a lot more sense. So
Okay.
I don't know if anyone...
Well, I've posted the Hewitt-Druitts.
Yeah.
I posted the Hewitt-Druitts. That was one of the reasons I went back to Blackboard.
Yeah.
Is that I wanted to show you that I've posted the Hewitt-Druitts. So what we've done is all we're using X for. And literally, guys, if it makes more sense for you to do this, and really and legitimately it does, okay? For a lot of you, if it makes more sense to say position, that's my position, is equal to my velocity times my time. If it makes more sense to actually write out the words, okay? If it makes more sense. And then that's plus my 1/2 my acceleration times time squared. If that makes more sense to you, do it. At least initially. Because you're going to get tired of writing out the words. You just fundamentally get tired out the words. That's why we go to symbols. Because I like to write one little thing instead of writing out the word position every time. I like to write out one little piece. When you write these out, so this is my change in position is equal to my velocity times time plus my 1/2 my acceleration times time squared. My knowns, or what my variables are, is my position, acceleration, and time. So if my problem is giving me, I'm looking for the position, but I know the acceleration and I know the time, and a lot of times it's telling me I'm starting at rest, or I'm starting at 10 miles an hour, or I'm starting at 5 meters per second. That's what this is telling me. It's my initial position. It's my initial position. My velocity squared is equal to my initial velocity squared plus 2 times my acceleration times my change in position. This one does not have time in it. So when I have a problem like I just had with my airplane, I didn't know the time. I had no idea what the time was. No idea. So I can actually go in here and say, I don't need to know the time in order to solve my problem. This one gives me a way of solving the problem without the time. Then, if I have just this one has got just velocity, acceleration, and time. I don't need to know my position at all. We do this one all the time when you're passing a car, right? If I'm out there on 412 and I'm traveling at 55 miles an hour and I want to pass another car, I know I'm going to have to speed up in order to be able to pass the car, and I make a mental calculation as to exactly how I'm going to do that. And I make a mental calculation as to exactly how I'm going to apply the accelerator. So I'm not doing anything that you guys aren't already doing. All we're doing is putting a mathematical equation to it. That's all we've done so far.
The problems we always have the three variables, or will we have to?
Sometimes you have to calculate the variable from something else. And when we get to 2 dimensions, which we're about to do, we can use information from one dimension to give us information about the other dimension. So so the question was, do we always have those 3 variables? So let's look at a problem real quick because of that question. Let's look at a problem. I'm going to roll a can off the tabletop. Okay? I'm going to roll a can off the tabletop. We know that my can, if I roll it off the tabletop, is going to follow that kind of path, right? We know that. We've done it. If I were to take her water bottle over here, we would roll it and we would know it's not going to fall directly underneath that if I roll it, okay? Because if I roll it, it has a velocity. It has a velocity. And that velocity, let's go ahead and give it a velocity. We'll actually give it and define one. Velocity is 0.5 meters per second. We're rolling that object off the tabletop, 0.5 meters per second. Now, we know that if I just drop it, right? If I just drop it, it's got an acceleration due to gravity that's going down. And it's going to take a certain time to go down. If we know that the tabletop is 3 meters, okay? If we know the tabletop is 3 meters, I can calculate that time. Because I know the height, I know the initial velocity in the y direction. Because my velocity in my x direction and my velocity in my y direction are independent of each other. And in fact, if I were to drop a ball at the exact same time that this object goes off the table, they would hit the ground at the exact same time, even though this went a distance away. They would actually hit at the exact same time. So I can calculate that time, so we can do this. So my change in position is equal to my initial velocity, and I am now going to use a subscript y. This is going to tell me my initial velocity in the y direction, and then instead of my position, I'm going to use h because it makes a little more sense for me, and that's the height of the table. My initial velocity in the y direction times the time of the fall, minus, because my acceleration due to gravity is in the negative direction, divided by 2, 1/2 at squared times squared. So that's the motion that I'm going to have in the y direction. That's the motion I'm going to have in the y direction. So I can solve for time. So this becomes 2, that's 0, because in my y direction I have no velocity when I'm starting. I'm just dropping it. And then so I've got 2h is equal to minus gt squared. But my h in this case is also in the negative direction, so I'm going to have a negative value there, because I can't have negative time, and the square root of a negative number is going to be kind of funky. So I know I've got to do something there, so that's going to help me with my direction. So I get 2h divided by g is going to equal my time squared, and now my square root of 2hg is equal to time. So if I plug in numbers, that's going to be 2 times the height, which is now going to be 3 meters. Or, yeah, well, that's the value I gave, 3 meters. And then that's 9.8 meters per second squared. Meters cancel, and I get second squareds under the square root. Square root of second squares is seconds. And now, if I do that calculation, I get 6 divided by 9.8. And that tells me I get 0.782 seconds is the time of fall. That's the time it took the object to fall. But if I want to find this distance from the bottom, we're going to call that d. D is going to equal my initial velocity in the x direction times time. But guess what?
Can you pull that down some?
Sorry. Guess what? There's no acceleration in the x direction. These are independent variables. There's no acceleration in the x direction. So if I do this 1/2 at squared, that part of the equation doesn't come into play because I don't have any acceleration in the x direction. So now that I have time, because I figured out the time using my information about the fall, now I can go in here, and we said it was going at 0.5 meters per second. Provided I don't have air resistance and friction, and I do it 0.782 seconds, it's going to end up 3.91 meters away from the table. And it's something that we've done over and over again. Would it help on Wednesday? Yeah. I mean, this is, you get independent variables. My x and y are independent variables. So now you guys understand why I harp on the vectors. So let's look at a vector for a second. So I've just got two vectors here. I just got two vectors. Let me see if I can scroll out. Okay, I got two vectors. Now, vectors are additive properties. I wrote my vectors out in terms of their vector components. Okay? I've got my A vector is 2 in the x direction minus 3 in the y direction. So there's 2 in the x direction minus 3 in the y direction. And I can draw this vector. Okay? This is just a mathematical representation of a vector, and I've just drawn that vector. I'm going to add this vector to it. I'm going to go over 2 in the x direction, but I'm going to go up 5. I'm adding head to tail to get my vector. Oops, looky. I didn't draw it very well. But I'm adding head to tail to get my vector. I can use a graph to do, I can use graphing, I can use a graph to do it. And this gives me my resulting vector. That gives me my resulting vector. So when I added those two vectors, this tells me my ultimate change in position. This gives me my resulting vector. We're going to see this again in forces. We're going to see this again in a lot of different ways. But I can add my vectors, and I add my vectors head to tail. I can do this mathematically. I added these two vectors. This becomes 4i. 5 minus 3 becomes 2j. And now if I look at my vector graphically, guess what? I'm at 4. 1, 2, 3, 4. And I'm up 2. 1, 2. So I've added my vectors graphically. And we've done this over and over again. How many times have you driven down 412 or 60 and this happens to you? All right? So I'm in my car and I'm going, and let's say I'm sitting here in my car or my truck or whatever. There's my truck, okay? So I've got my truck and I've got a velocity vector and I'm going 60 miles an hour because I'm the slow person in traffic, right? Most of us are doing it at 70, right? And it's good old Oklahoma, and it's good old Oklahoma in May, and we've got 40-mile-an-hour wind gusts. What do I got to do to keep my car on the road?
It'll turn turned towards the wind?
I got to keep my wheel turned towards the wind. I got to keep my wheel turned towards the wind. Because if I don't, where's my car going to end up? I'm going to end up in the ditch, right? Because what happens is I'm adding those velocity vectors, and I actually might end up this way if I don't let it, if I'm not keeping the wheel turned towards the wind. If I'm doing this from a hockey puck point of view, okay, if I have a hockey puck, and the reason I use a hockey puck is because I have very little friction, and it starts out at 5 meters per second, or 5 meters per second, and then it hits, or somebody taps it, so that it goes off, so it has another 3 meters per second. Those things are going to add up, and my hockey puck is going to go in that direction. If, we've all done this one too, okay, I got a river. And my river's flowing, we'll say at 4 meters per second. And I've got my little rowboat out here, and I'm only rowing at 2 meters per second. The actual boat's going to travel that direction, right? I'm going to actually travel down the river in that direction. And it turns out, if I add these vectors head to tail, if this is a 2 meter per second vector, and this is a 4 meter per second vector, a squared plus b squared equals c squared. So I got 4, so I get 4 squared plus 16, or 2 squared is 4, plus 16, square root of that is the square root of 20. I'm actually going to be traveling in this direction. If I do my square root of 20, at a rate of 4.47 meters per second, but I'm going to be going that way. And I can figure out this angle because we've learned that this is my adjacent, this is my opposite, and if this is 2 and this is 4, the tangent of the angle is going to equal 4 divided by 2. So the tangent of the angle is going to equal 2. My arc tangent gives me my angle. And that says, oops, I'm in radians because I was doing something else, sorry. That's one of the things you got to check on your calculator. That didn't make sense. I'm at 63.4 degrees. So that's why we add vectors. Now, the reason we do this is because now if I'm in 2 dimensions, and I've got a vector, and what we're going to have here is we're going to have my cannon, and I'm going to actually show you a cannon here in just a second. We're going to have a cannon, and my cannon is going to form an angle of 30 degrees. And we shoot a cannonball out of that cannon. We know what happens, right? It's going to follow a path that looks like this. It's projectile motion. It's going to follow that kind of a path. But I need to know the velocity in the x direction, and I need to know the velocity in the y direction. Because the behavior is independent of each other. I'm going to need to know those different pieces. And how I'm going to figure that out is if this is 15 meters per second, and I know that this angle is 30 degrees, my vector x component is going to equal my 15 meters per second times the cosine of 30 degrees. That's the magnitude of the vector in the x direction. Or if I look at it mathematically, that's the projection on the x-axis. If I do the y component, It's 15 meters per second times the sine of 30 degrees. And I'm going to get those individual components, and that's going to help me solve the problem down the road. It's going to actually help me solve the problem down the road. So that's why we harp on vectors so much, is because when I get to 2 dimensions, I've got to be able to break apart my x direction and my y direction because they're independent variables. Okay, so let me go back here. All right, so you should see, if I go into Blackboard, just a second. Let me get back there. Okay, now.
Are we still able to get into our quiz 1?
Oh yeah. You should be able to get back into quiz 1. Oh, and that's another thing. We had an update in Blackboard right before school started, and I know that several people have had trouble when they've opened up the quiz and have not seen anything. You open up the quiz and you say quiz start, and nothing's there. That's one place that people have had trouble. There's another place that people have had trouble if you've gone into WebAssign and you try to open up your book and nothing happens. There's been a change in Blackboard. You need to probably check your browser settings. Your browser settings may not have the latest and greatest updates. And one of the places that you can go to see whether or not your browser settings are set up right is you can click right there, and you can make sure that you have allow for JavaScript, allow for Flash. You can actually do allow for pop-ups. Some of the changes that have happened, that the Blackboard pop-up and your browser aren't working together correctly. So if you're having trouble when you're accessing something, double check. And I've had my chemistry classes are in Connect, and they've been having similar type problems in Connect. So if you're having trouble in Connect, you're having trouble in Blackboard, you're having trouble in WebAssign, you're having trouble somewhere, double check to make sure that you've got the right things allowed. And you may have to clear your cookies and come back in order to get it to work. But that is something that I've helped a lot of people over the last week, because there's been an update in Blackboard and some other things that have been going on. But I went and talked to our IT people about it. So if I go to week 3, this is our week that we're in. And really, honestly, this is she had mentioned Hewitt-Druitt. These are Hewitt-Druitts. And I strongly recommend, if you're having some trouble, Hewitt-Druitt, he draws things and he talks through things really, really well. And it's like velocity vectors, showing the different vectors, and he does it on a conceptual level. And his conceptual physics book is pretty readily available. So I've posted the ones that kind of make sense. So I've got the velocity vector one in here, where he's showing the velocity our airplane is taking off, just like I did with the car. And it's just, having somebody else say it sometimes makes more sense. Remember, your mother tells you that 20 times, you don't listen to your mother. But if your buddy tells you the same thing, you listen to your buddy, sometimes that works. It sometimes does. Also, if you're having trouble, honestly, study buddies are big time, okay? Getting through and learning that now is going to help you as you go on to your senior and higher level classes, because it really is going to make a big, huge difference if you've got your study buddies. So you want to so I've got the Hewitt-Druitts in there. We're going back here. Okay, so I've got the free fall one, where he's dropping a ball and he's showing the acceleration of the ball falling. I've got the vector one, and then we're about to get to this. I've got the projectile motion simulation here in just a second. So we'll actually look at that here and just start looking at our projectile motion. So those I've added to Blackboard so that you guys have quick access to them. The other thing is this, and I brought it with me today. If I go to the document camera, the OpenStax physics book that I have for you, or I gave you the information to. Let's see if I printed out the different page here. It has a little bit more information. So if I go here to the OpenStax, scroll in here, it gives you a little bit, or little different pictures, little different examples, writes out the equations or develops the equations a little differently. This may make more sense to you. For some of you, the way this author does it may make more sense than the way our author does it. But it's the same types of things that we're doing. We're adding vectors. Vectors can be added head to tail. And we're dealing with the equations just a little differently so that you guys can play with the equations a little differently. So when we look at them and use them and figure them out, I use the general equations to start with. But the way they actually present it in the OpenStax book might just be a little better for you. So let's look at those equations again, because I want to do one thing real quick so that you guys can kind of look at it. So my general equation, if I'm in the x direction, change in position is equal to, whoops, got to scroll out. My change in position is equal to my initial velocity times time plus 1/2 AT squared. And then I had velocity squared is equal to my initial velocity squared plus 2 times my acceleration times my change in position. And then I have velocity is equal to initial velocity plus AT. Those were our general equations. Now if I write them for x, all right, I write them for the x direction, and then I write them for the y direction, and this is only good when I have a constant acceleration, and that constant acceleration is gravity. All right? So I'm going to write these for the special case that I've got, that when I have a constant acceleration, and the only constant acceleration that I have is this acceleration due to gravity. So this is general with a constant acceleration. So anytime I have a constant acceleration, like in my car or that airplane that's taken off, and I'm trying to figure that out, this is a constant acceleration, and that I can use in any case, as long as my acceleration is constant. If I have a variable acceleration, can't do it. This only works when I have a constant acceleration. This is when we start dealing with motion in 2 dimensions, and my motion in 2 dimensions, the only acceleration that I have is gravity. So if I do that, I look at my change in x. If my only acceleration is due to gravity, gravity is only in the y direction. So what happens is I get a change in x is equal to my initial velocity in the x direction times time. I have no acceleration in the x direction, so I don't have that term. Then guess what happens? That's the only equation I have in the x direction. Because this one, all that's saying is that my final velocity squared is equal to my initial velocity squared in the x direction. My final velocity in the x direction is equal to my initial velocity in the x direction. I don't have any acceleration in the x direction, so I'm not going to get a change. But what happens in the y direction is a little different. My change in y is going to equal my velocity in the y direction times time minus because my acceleration due to gravity is in the negative direction, so I have to worry about that negative sign, divided by 2. And a lot of times we use h to be my change in y. H meaning height, okay? A lot of times we use h to mean that, for that. So then, if I do this, my velocity final in the y direction squared is equal to my velocity initial in the y direction squared plus 2. I've got to put a negative g in here, and if I'm going to use h for my change in y, I get that equation right there. And I can rewrite that as velocity final in the y direction squared is equal to my velocity initial in the y direction squared minus 2gh. And then if I do the last one, I get velocity final in the y direction is equal to the velocity initial in the y direction minus g times t. So these are just the exact same equations as this up here, except now I've written them so that I've separated them out for the two different dimensions.
Wouldn't the initial velocity in the y direction be gravity?
Gravity is in acceleration, meters per second squared. Velocity is in meters per second. So the question was whether or not gravity and the initial velocity are the same. Acceleration is meters per second squared, so the units are different. And the initial velocity is going to be in meters per second. That's why we use our unit analysis to help us out. Because that way we know we've got everything straight. That's also why we know this is a velocity, because if I look at my units here, I get meters per second squared times seconds. One of those seconds cancel out, I get meters per second. Okay? Everybody with me? Is it starting to make more sense? Okay, yeah. And really what's happening is now we're using the language a little bit more. I mean, it's the same stuff. We haven't really changed anything. It's the exact same stuff. And we've got it. So one of the things you can do, so there's my cannonball, right? There's my cannonball. We can break it up. We can play with our vectors. And then we can do fun things like this. So I'm going to switch. Okay, in here. I'm going to clear it. I'm going to erase everything. I'll move this over. We got a cannon. I have provided for you guys, if you go over here, this is the projectile motion simulation. If you click on it, if you click on that little link, it's going to take you right there. And all I've done is clicked the little start button, and that's where I'm at. And then I played with the cannonball. Okay? I played with the cannon. So we can start with, the first thing is that when you guys do this, we're going to make the assumption that we have no air resistance. This actually figures in air resistance for us. And so you want to, if you play with this, you're going to want to check the box to make sure you don't have air resistance. Okay? Because we're going to do it without air resistance. And I've got the cannon set directly up. Okay? This is just like the ball toss that we did on Wednesday, right? I did the ball toss problem on Wednesday. So this case, we're going to have the cannon shoot a cannonball straight up, and it's going to come back down. All right? So we're going to do that. And I'm going to shoot the cannon, and it goes back up, and it comes straight back down. And because it's a nice simulation, and we don't have any wind, and we got it just perfect, it goes exactly straight back up, and it comes straight back down. So one of the things that we can figure out is how high did the cannonball go? Okay? How high did the cannonball go? Now, this is a case where I'm still in one dimension. I've only dealt with one dimension. So we're going to calculate how high the cannonball went. Okay. And I'm going to have my height is equal to my initial velocity times time plus 1/2 minus gravity times time squared. Well, that's one of my equations. We knew from the problem that my initial velocity is 15 meters per second in that direction. We've got my acceleration due to gravity, which is a negative 9.8 meters per second squared. But I don't have time. So this equation is not going to help me out because I don't have time. Well, I have another equation I can go to. I can go to the velocity final is equal to my initial velocity minus my acceleration due to gravity times time. I know what the velocity at the top is. Velocity at the top has to equal 0, but I still don't have time. So I've got another one I can play with. My velocity squared is equal to my initial velocity minus 2 times gravity times the height. So now I know what the velocity at the top is. I know what the velocity I started with was. I've got my acceleration due to gravity. The only thing I don't know is the height, which is exactly what I want to find. So that's good. So now I get my velocity at the top is 0. My velocity when I start is 15 meters per second, and I've got to square that. Minus 2, 9.8, and that's in meters per second squared. There's my height. So I'm going to get 15 meters per second squared divided by 2 times 9.8 meters per second squared. This is going to leave me something in meters, which is good because my height is going to be in meters, and that's what I want. So I plug that into the calculator, I get 15 squared divided by 19.6. I get 11.47 meters. Now if I go to my simulation, I can go to my simulation and go back here. So there's my, I can go to the simulation. There it is. And it gives me a tool, a handy dandy tool here. I got a handy dandy tool that I can actually measure my handy dandy with my handy dandy tool. So I'm going to measure, I'm going to start there. I'm going to put this up here at the top. Actually measure it. And if my eyeball is just right. There we go. I get 11.48 meters. And some of you might say, well, that's all well and good. Right? That's all well and good. Is that really how it works in real life? Guess what? It's really how it works in real life. Because I also have for you this right here. I'm going to expand this. So I've actually got set up in my office a meter stick, which is what's in there. You're going to actually get to see the video. Now, it is a little popper, smiley popper, okay? And the only part that's not going to work really well is the fact that I have to eyeball it for my image analysis software. But this is a real thing that was done in my office. So so we go the popper, and because it is a real popper, it doesn't go perfectly straight up and perfectly straight down. But I can actually this is the actual video of the data that you're about to see. So let's look at it again. I go up and it comes straight back down. So whether or not I can perfectly get the image to see it and perfectly get it on there, I have to make that assumption. So what did I do? I've got this. Let's go to the slideshow here. that's my video. I've used my video analysis software. It's if you guys want the software, holler at me because it's free. It's tracker software. It's free on the internet. There's actually right now there's some really good apps out there for tracking, but this is a really nice one. But I used it. So what I did is I went in there and I actually marked the positions, and you can see how I marked the positions, and I got a nice curve. And in this case, it's going to, and this case I'm using it and I'm making the assumption that I'm only in one dimension. Even though I'm using the curve that I get looks parabolic, it's not a projectile motion in this case, it's just still one dimension. Now let's look at the equation. When I plug it in and actually plot it, which you can do either in this software or you can do in Excel or you can do it on a piece of paper, I actually get a line that looks like this. That my curve is described as y is equal to a negative 4217 x squared plus 2723 x minus 192. Well, if I look at this and I look at my equation, there's my change in position. With respect to, this is my change in position. I just happen to have my initial position, my initial velocity, and 1/2 AT squared. My x on this graph is time, not x. I'm just using the variable to plot it. I can actually look at this and it tells me that my acceleration divided by 2 is a negative 4217. Turns out that this is in millimeters. I'm actually in millimeters. And if I actually look at that, if I take 9.8 divided by 2, I should have like 4.4. What? 9.8 divided by 2? Let's see if I didn't do that right. 9.8 divided by 2. I should have about 4.9. Sorry, I knew I didn't do it right. I should have 4.9. Well, again, this is actual experimental data. I got 4.2. I can almost get gravity by reading it off the graph. So if you want to look at it, I can plot velocity. This is if I do a free fall experiment. I plot velocity, and in this case, I'm going to have my velocity equation. I can write my velocity. My initial velocity is plus 1/2 AT squared is going to equal my final velocity. I've used the same data, actually plotted it, and it shows me that I get gravity at negative 9.2. Well, experimental error. I also have air resistance. I also have a few other things that are going on in this. One is picking out the data straight from the video. But I got a pretty good job of getting gravity just by doing a popper experiment in my... So, one time I did this, somebody says, well, what kind of questions might I see related to this data? Is that a spring popper is allowed to pop. It can be represented as one-dimensional motion. During the pop, it reaches a maximum height of 28 centimeters at a time of 0.34 seconds. What's the initial velocity when the popper was released? Go back in, use my equations that I've been using, and I can calculate that. So I can do it. Another one is that it takes 0.34 seconds to fall back down. Remember, I have symmetry. What goes up has got to come down unless I'm not at that even level. Okay? Unless I'm not at that even level. And then I can have it accurately reported in one dimension. So those are some kinds of questions that you might see describing the motion of my little popper that I have. So you can actually see that that's real data. So what happens to us now is now I can go back to my simulation and now I can play with it. Okay? I can play with it. So I'm going to use this one here, and instead of having my Canon, I've got my Canon at 50 degrees now. we're going to start with the same velocity, initial velocity, except now it's going to be, I'm going in the X and Y direction, and if I let the cannon go, I get my nice projectile motion. Okay? I get my nice projectile motion. So we can start calculating how far downrange something is. We can calculate the height or the maximum height. We can calculate the different times that it takes, and we can start looking at different positions along the way. So at time is equal to 1 second, I can use the little graph gizmo and have it actually tell me. So you can play with this to start looking at how my arrangements are. You can also look at the velocity vectors and my acceleration vectors. So that if I put my velocity vectors in, and we're going to let it go again, you can see the vectors change as we go through. So you can actually look at the vectors. I'm going to have it go again. You can see the direction of the X vector. You can see the direction of the Y vector. And you can look at varying points on there. You can look at the acceleration vector. I only have the acceleration in the Y direction. And it's constant throughout. So you guys can actually play with this in order to have it kind of work through it. And then you can play with it and add to things like air resistance, because this is without air resistance. So you can do things like this if we want to hit the guy, right? And you actually have a homework problem that the question is, where do I have to be in order for it not to hit? So you can play with it. Something to play with. All right. I'm going to do one more problem, and then we're going to call it a day because I'm pretty sure brains are full. I'm getting that glazed look. I'm getting that glazed look. So we'll do one more problem here, and then we'll be done. All right. So what we got here is I've got an airplane, kind of Dr. Seussian here, Dr. Seussian airplane. And our plane, let's say, is traveling at, we're going to go ahead and do this at 100 miles per hour. So our plane is traveling at 100 miles per hour. It's going to drop a package. So our package is going to travel like this. And we want to hit the target zone for the we're going to drop a package. It's like we're on the island and we're getting our care package. And we want the plane to drop the care package. We want to know the distance away that he has to drop the package in order for the package to hit the target. Right? So it's pretty much exactly what we did just a second ago. And we're going to be flying at an altitude of we're going to be a little low. We're going to be at an altitude of a half a mile. So I'm going to actually use English units. So we want to know how far away we have to drop the package. Well, the way to figure that out is I got to know the time. So I'm going to use my Y direction to help me calculate the time. The height is going to equal my initial velocity in the Y direction times time minus gravity divided by 2 times time squared. And if I looked at my handy dandy little sheet that I derived those equations, it's that equation right there. there's no velocity in the y direction. I'm only traveling in the x direction when I drop the package. So now, that height, of course, is down. So I have to make sure I have my negative in there, because that's my negative height. So now I get, my negatives will cancel, so I get 2h divided by g. The square root of that is going to equal time. So if I do this, I'm going to get 2 times 0.5 miles. Oops, my g is 32 feet per second squared. If I'm going to work this in miles, and I'm going to have to put this in miles, so I got feet per second squared. I have 1 mile is 5280 feet. My acceleration due to gravity in miles per second squared. 32 divided by 5280 is 0.00606, and this is miles per second squared. I probably need it in hours, right? So I'm going to need 0.00606, and I'm going to do, this is miles per second squared, and I have, it's 3,600 seconds per hour, and I have to square that. And if I've punched everything in the arithmetic okay, I get 3,600 seconds. Seems awfully big. 60, 3,600 squared times 0.00606. I'm getting a number like 78538. And that's miles per hour squared. Weird acceleration number, but that's what I got. And I get 78538 miles per hour squared. I get 1 divided by that. I have to take the square root of it. And it tells me I'm at 0.00356 hours. So that's when I have to drop it. When I'm 0.00356 hours away from the target. If I'm traveling at a half a mile out at 100 miles an hour, which kind of makes sense. And now my distance is equal to my velocity times time. My velocity is 100 miles an hour. And I've got that times my 0.00356 hours. I have to drop it at 0.34 miles away. That's just because I picked funky numbers. But you have a problem just like this one. And you have an example in the book just like this one. Alrighty. See you guys Wednesday. You have a quiz due Wednesday. And we'll work some more problems.
I studied like. Did you? I studied. pretty sure.